I will sketch out our transformation. So this will be our X, Y, and this is our Z. Okay. Then I'm going to sketch our centroid. Okay. And now the moment is applied in such a way. Okay, I'm going to sketch our applied moment. Okay. So this is our applied moment. And then this is our direction. Okay. And it has a certain angle over here known as theta. Okay. And this theta over here, I'll emphasize down here, this theta over here is rotating, okay, rotating about the YZ plane. Okay. So now, when this is the case, we will ask ourselves, now, why is this known as unsymmetrical bending? Okay, so the next question we usually tend to ask ourselves, okay, I just showed you symmetrical bending. So the next one, we also will ask ourselves, why this is also known as unsymmetrical bending, right? I know, I understand, right? You will also know that, hey, Eugene, this is it because the formula is different. It's my over I minus mz over izzzy. Okay, but I would like to show you why we classify that, like why we classify it as unsymmetrical. And again, whether it's symmetrical or unsymmetrical, it's all dependent on the stress field. Okay, so for this case, it's unsymmetrical. So what do I mean by stress field? Okay, so we are going to draw the cross section again. So I'm going to sketch the cross section. Y, Z. This is our rotation X. Then this is a cross section, okay? Okay, so that is our cross section. I will sketch our axis where the centroid is. This is purely by observation. Okay. So over here, this is how our moment is applied. Okay, so this is our moment. Now the moment over there can be broken down into its component. Okay, M can be broken down into its component. And we know this angle over here is our theta angle. Okay, and this moment can be broken down into two components. Okay, so what do I mean broken down into two components? So it can be drawn let me. So this is again our z axis. This is our y axis. Right. So what do I mean can be broken down into two components? So one component over here, which I'm going to use in orange. Okay. So this is our MZ. Okay. And there's also a vertical component. And this is our my. So if we were to use our right hand rule, right, mz will be in this direction, right? So you just use your right hand rule and the thumb points the direction of the arrow and your finger that is grabbing. Don't close it, okay? If you close, the thing will start to rotate. Just grab, okay? If you grab it, this is how mz will look like, and then my, okay, will be in this direction. Right, when you grab it, there is your my direction, okay? Then we are going to label this point as alpha, beta, I, and j. Okay, we're going to label it that way. And I want to apply what I've taught you, right? So if we look at mz, the head of the moment vector is under compression. The tail end is under what? Tensor. Likewise for my, the head end is under compression. The tail end is under tensor. Okay. So now, if we are going to look, I'm going to create a table. Okay. So the table is we are going to have a point alpha. Okay. We're going to have points. We're going to have alpha, beta, I, and j. Okay. And then what we're going to do, the next column, we are going to find stress x will be equal to mz over izz multiplied by y. Okay. The focus over here, let me use orange, okay, so you can. So stress x is equal to mz over izz multiplied by y. Okay. So I want you to focus on the bottom diagram. Okay. I want you to look at mz, the orange color one. Okay. And I will also label over here alpha, beta, I, and j. Okay. And as you can see, right, point alpha, right, we have to look at, I want you to focus on mz, and at point alpha, we know it's under compression. Okay, we know it's under compression. Can you all see that? Yes or no? Right, we know it's under compression. Right, because if we look at mz, right, above the zz axis, anything above the zz axis is under what? Compression due to mz. If you look at point beta, again, due to the loading of mz, is also under what? Compression. And compression, we tend to give this negative. And at point I, due to mz, is going to be tensor. Okay, positive. And j is also tensor, positive. Now, again, this is due to mz. Anyone have any question regarding this? This is a I'm doing this based on moment vectors and not focusing on whether the formula is positive or negative. Okay, you understand what you can understand why it's under, why we have it as tensile. or compression. Anyone have any questions so far? Okay, I don't hear anything, means you understand. Okay, so now I'm going to do, okay, you can see more by examples. We are next going to do, we're going to deal with the pink one. Now this is stress X is equal to my over Iyy multiplied by Z. Okay, we're going to focus on my now. So at point alpha, I want you to concentrate on the pink. Okay, so now this is tensile, and this is going to be positive. Okay, and beta due to my is going to be compressive, which is negative. Okay, and then point I, you can see, is under tensile, which is positive, and then point J is compression, that is negative. Okay, so what we can see down here, if we were to apply the, or if we were to combine the formulas together, okay, so the last one, if we were to combine stress X is equal to my over Iyy, okay. Now I'm not so worried plus or minus. I'm not so worried down here because we already, based on the moment vectors, we already know that whether is it positive or negative. Okay, so this is mz over izz multiplied by y, and we can see at point beta we will have our maximum what, compression, right? Because it's the only point where you have negative stresses in both moment acting the z and moment acting in the y-axis. And at point I is the position where you have maximum what? Tensile. Okay. And we know for the fact that at point alpha, we know that point x alpha will not be equal to point x beta, due to the fact that moment about z will induce a compression, moment about y will induce a tension. Okay, and likewise at point J, we know that stress X at point J will not be equal to stress X at point I. Okay, so under this condition is what we call unsymmetrical or centric unsymmetrical bending. And once again, whether is it symmetrical or unsymmetrical is all dependent on your stress field. You can see that, right? It's all depending on your stress field. Okay. So another thing I want to highlight is your M. If to find your my, note that my is equal to m sine theta, and mz is equal to m cos theta. Okay. So this is why we call unsymmetrical bending. Okay. So now I'd like to highlight an important point where students tend to make, or not just students, engineers will also make the same mistake. Okay, so I will elaborate more on this formula in terms of second moment of area. Okay, so let me get the formula. Okay, so I already wrote down how you calculate my and mz.